In this lesson, we're looking at ways that we can use trigonometry to problem solve in ways that maybe you haven't thought of before. So consider finding the area of a triangle. So in this example, we're asked, suppose we draw an altitude AD to side BC of triangle ABC. So they've done that here. Write an equation using trig in terms of angle C, the height of H, and one of the sides. So if I look at this triangle here, notice now there's also this triangle. And so I can, if I'm trying to solve for H, and I know side B of the triangle, then I would be using the sine of C, and that would equal H over B. In the next step, they're asking us to solve this equation for H. In other words, get H by itself. So I multiply both sides by B. So H equals B times the sine of C. And so in part C, they're asking us to complete this formula for the area of triangle ABC, that's this triangle, in terms of H and another of its side lengths. Well, remember that we know that the area of a triangle is 1/2 base times height. Oh, hey, I just found the height. A is my base, so area equals 1/2 times my base is A, and then my height that I just solved for was B sine C. And I kind of got ahead of myself, and I did step D already in step C, but here is kind of the bottom line of this explore problem, a different formula for the area of a triangle. So does the area formula we found work if angle C is a right angle? So let's consider. The right angle would be here, so this would be 1/2 A times B times the sine of 90. Well, in this right triangle, A would be my base, B would be my height, so, what about this sine of 90? Well, let me type that into my calculator. The sine of 90 happens to be 1. So, yes, since sine 90 equals 1. Suppose we used a trig ratio in terms of angle B, H, and a different side length. How would this change our findings? What does this tell you about the choice of sides in the included angle? So if I had looked at angle B instead of angle C, then I would have called this sine B equals H over C, because I would be using this right triangle. And that means that the height would equal C times the sine of B. And I could still use A, so that would be that the area of the triangle would be 1/2 AC times sine B. So what were they asking us? How would this change our findings? The equation would look a little bit different. But the same idea. 1/2 times the product of two sides times the sine of the included angle. Sorry, that's not very clear. But those of you that listen to videos as well as watch them heard me say included angle. So here's the formula, and they have it 3 different ways, but it's all the same idea. So in example 1, they're finding the area of the triangle. This is the angle that I know. It is included between the 2 sides that they gave me, so they just plugged it right into the formula and used the calculator in order to find an answer. Part B, we're doing the same thing, but I don't have a diagram. So let's sketch one. All right, so here's angle D at 57 degrees. DE is 9, DF is 13. So I know 2 sides and the included angle, and we plug the values in. So 1/2 times DE times DF times the sine of D. We substitute the values in. DE is 9, DF is 13, and angle D is 57 degrees. The rest is just typing into your calculator. So 1/2 times 9 times 13 times the sine of 57 is approximately 49.1. Similar idea in problems 3 and 4. I have 2 sides and the included angle, so I know the area of the triangle will equal 1/2 times 12 times 15 times the sine of 34. And the rest is just a matter of plugging into the calculator. So 1/2 times 12 times 15 times the sine of 34 is approximately 50.3 square millimeters. And number 4, I know 2 sides. I know the included angle. I plug the values into the formula. Area of the triangle will equal 1/2 times 3 times 6 times the sine of 108. So plugging that in gives us approximately 8.6 square centimeters. Next, we're looking at solving a right triangle. And as you can see in your notes, solving a right triangle means finding all of the lengths and all of the angles that I didn't already know. All right, so in order to do that, you have to know that it's a right triangle, and you have to know either 2 side lengths or a side length and an acute angle. And so in this diagram, I know 2 side lengths, and I'm asked for the other side length. So notice how they're using Pythagorean's theorem, just like we've done in the past, to find the 3rd side length of the right triangle. And now what we're going to do is find the angle measures, just like we did 2 lessons ago. We're using inverse trig ratios. So in order to find angle A, I'm going to use a cosine ratio because 7 is the leg adjacent to A and 9 is the hypotenuse. So cosine of A equals 7 over 9, which means that the measure of angle A is the inverse cosine of 7/9. So when I type that into my calculator, I take the inverse cosine of 7/9 and get that it's approximately 39 degrees. I know that angle A and angle B are complementary, so that means that they add up to 90. I substitute in 39 for angle A, and then I subtract that 39 from both sides, and I find that angle B is 51. Is it possible to find angle B before I find angle A? Sure, because I would use the sine of B equal to 7 over 9. And I would use the same process that I did back here, inverse sine. In the your turn example, we're doing kind of the same thing, except this time I wasn't given two side lengths. I was given a side length and an acute angle. So in part 6, or number 6, they're asking us to set up a trig ratio and find the distance EF. So EF is the leg adjacent to the 27 degrees. The 33 is opposite the 27. So I'm going to use tangent of 27, and that's going to equal 33 over EF. Remember that if I think of this as a proportion, I can switch things across the diagonal and get that EF is equal to 33 divided by the tangent of 27. And when I type that into my calculator, I get 64.8. It asks me to use another trig ratio to find the length of DF. So I could use this 64.8, but I would advise you against it, and here's why. This is an approximate value. This 33 that they gave you is exact. Use an exact value whenever. 33 is opposite, DF is hypotenuse. Once again, I can switch things across a diagonal and get that DF is equal to 33 divided by the sine of 27. And that will be 72.7. And then finally, they're asking us to use the fact that acute angles of a right triangle are complementary to find the measure of angle D. Okay, so measure of angle D is 90 minus 27, so that's 63. Next, we're looking at solving right triangles in the coordinate plane. So in part A, I have triangle ABC, given these coordinates. Notice they plotted them. And then find the side lengths to the nearest hundredth and angle measures to the nearest degree. So notice that we can easily find AB and BC by counting the lengths. See how they used distance formula to find the length of AC. They could have also used Pythagorean's theorem, because that basically boils down to the same thing. And we know that AB is perpendicular to BC, so that's 90 degrees. And then they used tangent ratio to find angle C, subtracted that angle from 90 in order to get angle A. Same process in part B. So let's start by plotting the points that they've given us. -4, 3, 0, 0, and 3, 4. So that's F, this is E, D. When I connect my dots, here's my triangle. Oops, I labeled this wrong. This one's F. This one's E. Sorry about that. So they tell us here that angle F appears to be a right angle. So we would check using slope. The slope of DF would be 0 minus 3 over 0 minus -4. So that's -3 over +4. The slope of EF would be 0 minus 4 over 0 minus 3. And this is -4 over -3, which is +4/3. And they are opposite reciprocals. So angle F is 90. Now we're going to find the side lengths using distance formula. DE, that's the segment here, is 3 minus -4 squared plus 4 minus 3 squared. So 3 minus negative 4 is 7 squared is 49, plus 1 squared is 1. So I have square root of 50. And then they go through the process of simplifying the radical just to evaluate it anyway. I don't see any reason to do that. Let's just take the square root of 50 and get 7.07. Now we're going to find the length of DF. That's this segment here. And that's these coordinates up here. So DF is 0 minus negative 4 squared plus 0 minus 3 squared. This is 4 squared is 16 plus negative 3 squared is 9. 16 plus 9 is 25, and the square root of 25 is just 5. Finally, I'm going to find the length of EF. That's this segment here using these coordinates. And that is 0 minus 3 and 0 minus 4. So I end up with the same 25 and 5 there. In order to find angle D, they're using the sine ratio. So angle D is the inverse sine of EF over DE. The length of EF was 5. The length of DE was approximately 7.07. So when I take 5 divided by 7.07 and I take the inverse sine of that, I get approximately 45 degrees. Angles D and E are complementary, so angle E will equal 90 minus 45, which is also 45. How does the given information determine which inverse trig ratio you should use to determine an acute angle measure? We've talked about this before in class, that the combination of side lengths i.e. Opposite, adjacent, hypotenuse, determines what trig ratio to use. Finally, one more example like that. Take the points and plot them. 3, 5, that's J. K at negative 3, 2, and L at 5, 1. Oops, not there, silly. There. In this diagram, angle J looks like it's a right angle, but you have to verify it. So let's find the slope of KJ. So that's 2 minus 5 over negative 3 minus 3. Remember, y minus y over x minus x. So that's negative 3 over negative 6, which reduces to positive 1/2. I find the slope of JL. That's these 2 points. 1 minus 5 over 5 minus 3. That's negative 4 over 2, which is negative 2. and these are opposite reciprocals, so yes, angle J is my right angle. Now we're going to use distance formula in order to find the lengths of the sides. So JL is 1 minus 5 quantity squared plus 5 minus 3 quantity squared. And hopefully you'll forgive that I did y's before x's. It's kind of a habit after doing slope. It doesn't matter since I'm adding them. And for example, 2 plus 3 is the same thing as 3 plus 2. Okay, so hopefully that doesn't mess anybody up. All right, so I'm simplifying this, and I get negative 4 squared is 16, plus this is 4, so 16 plus 4 is 20. So the square root of 20 is approximately 4.47. JK is, I'll do it right this time, negative 3 minus 3 squared plus 2 minus 5 squared, and that's the square root of, this is negative 6 squared, which is 36. This is negative 3 squared, which is 9. 36 plus 9 is 45. And the square root of 45 is approximately 6.71. Finally, the length of KL is the square root of 5 minus negative 3 squared plus 1 minus 2 squared. This is 8 squared is 64 plus negative 1 squared, which is 1. So this is square root of 65, which is approximately 8.06. Finally, let's find an acute angle measure. I'm going to find the measure of angle K. And because I know all three sides, I can use any trig ratio I want. I'm going to use the tangent of K. So tangent is opposite over adjacent. JL was 4.47. JK was 6.71. So the measure of angle K, let me zoom out here, is going to be the inverse tangent of 4.47 over 6.71. That's approximately 34 degrees. Measure of angle L is 90